Hello everyone. So today we shall see the basics of filter design, and within that topic the first subtopic we shall see is about the linear systems with generalized linear phase. Okay, so we shall see the significance and definition of each and every term in the title of this topic. So in many cases while designing the filters and other signal processing systems that pass some portion of the frequency band undistorted, it is generally desirable. Two things are desirable. First of all, that the it should have the approximately constant frequency response magnitude, and the second thing is the zero phase in that band. So these two things are desirable whenever we pass the signal in some portion of the frequency band, and we want that the signal should not be distorted, right? But for causal systems, the zero phase is not attainable, right? And this we had seen in a couple of examples earlier. So some phase distortion must be allowed whenever we are talking about the causal system. Okay. Now, if there are some phase distortions, there could be the linear phase and non-linear phase. Okay, so we had seen a couple of examples also in the past that how do you define the linear phase, because generally it's a one-on-one mapping, which is not the case with the non-linear phase, and it induces more complications whenever we want to analyze the system or we want to analyze the properties of the filter, which induces the non-linear phase distortion in the sequences or in the signals. So it is generally desirable to design the systems to have exactly or approximately the linear phase. So in this subtopic we shall mainly focus on the systems which have the linear phase, and then we generalize it in the subsequent sections. So this topic is concerned with the formalization and generalization of the notion of linear phase. And the first, so let's give the name to this topic as system with linear phase. Okay, and the first system we will consider is the ideal time delay system. Okay, so we had seen earlier that the frequency response of the ideal delay time response is given by e to the power delay system, sorry, HID e to the power j omega is e raised to the power minus j omega alpha for mod omega lying between less than pi, or omega lying between minus pi to pi. So this alpha is real and not necessarily it's an integer, right? Second, and this ideal delay is, we assume that it is introduced by the communication channel, let's say. Okay, and this is of course is the ideal delay, the frequency response of the ideal delay system. So we had seen this system earlier, but just quickly analyze that what other properties are associated with these ideal delay systems. and how it contributes, or how we can see that it is under what circumstances basically it induces the linear phase or without distortion, and what is the impact of distortion. Okay, so seeing the frequency response, impulse frequency response of the ideal delay system, we had seen that it does has the constant magnitude response, and this magnitude response HID is given as 1. Okay, it has a linear phase also, which is given by phase of HID is equal to minus omega alpha. And finally, the constant group delay, which is given as GRD HID is equal to alpha, because it is the negative of the derivative of the linear phase, which would be alpha. So seeing the time domain response of this frequency response, it is given by HID of n sine pi n minus alpha by pi n minus alpha for n lying between minus infinity to infinity. Okay, and suppose if there is some signal x of n passes through this ideal delay system, then the response of the system with respect to this arbitrary sequence xn is given as yn as equal to the convolution of these two functions hidn, and this convolution can be explicitly written as the summation from k minus infinity to infinity for x of k sine pi n minus k minus alpha divided by pi n minus k minus alpha. Okay, so we had mentioned here that alpha is not necessarily an integer, right? If you recall, in one of the previous lecture we had seen that if alpha is equal to some nd and this nd is an integer, okay, in that case you would have HID of n can be represented by a shifted impulse function as delta of n minus nd. Okay, and for some arbitrary input xn, your yn would be given as x of n minus nd. Now the second one, if alpha is not an integer, then you cannot directly shift this sequence. In that case, you need to do the continuous time processing of discrete time signals. And this we had done earlier in the past, that if some input xn is considered, then first of all it is passed through some discrete to continuous time converter with some sample time, of course, and then it is processed through some continuous time impulse response, and then finally it is again converted from continuous to discrete time with some sample time t to yield the sequence y of n. Okay, and this we have labeled this in the past as h of e raised to the power j omega. So this signal is the continuous time input signal, and the output of course would be continuous time signal. Okay, so you can see this example we had also considered one example in one of the previous lecture where the shifting or this alpha was not an integer. So here this hc is the impulse function t minus alpha t, where alpha, note that, is not an integer, and hc of j omega can be written as j omega alpha t, so that you would have h of e raised to the power j omega as equal to e raised to the power minus j omega alpha for mod omega less than pi. Right? And then we can resample it to have this y of n as the sample signal xc of nt minus alpha t. So in this way you can process or you can carry out the operation of time shifting if the shifting or the if the shifting variable is not the integer. So here if we have alpha greater than 0, then we defined it as by time delay, and if alpha is less than 0, then generally it's defined as or it is named as the time advanced. Right? So this is with respect to the ideal delay, some of the basic property that we had seen earlier in the past. So based on this, now we shall consider a more general frequency response with the linear phase, and that general frequency response is given as h to the power j omega is equal to mod of h e raised to the power j omega times e raised to the power minus j omega alpha for mod omega less than pi. Okay, so this frequency response can be interpreted as for some arbitrary sequence x of n is first processed through the system which has the magnitude response with the magnitude response this and yields a signal wn, and finally it is delayed to yield y of n. Okay, this is just an interpretation of this. Now if we see the first part, let's say this one. So xn, what happens here that your sequence xn is filtered by the zero phase frequency response mod h e raised to the power j omega. Okay, and here in the second part what happens that whatever be the filtered output, that is w of n, filtered output is then time shifted. So we will use the generic term time shifted whenever we are doing the time delay or we do the time advance. So it is time shifted by the amount alpha, integer or non-integer, right? It could be integer or non-integer. So suppose we can consider one example. Suppose you have this h of e raised to the power j omega is the linear phase low pass ideal filter, which is defined as HLP of e raised to the power j omega as j omega alpha for mod omega less than omega c. So here we have reduced some cutoff frequency instead of pi, and a 0 for omega c less than mod omega less than or equal to pi. Right? In the time domain, HLP n can be defined as sine omega c n minus alpha and omega c n minus alpha. So here if I put omega c is equal to alpha, omega c equal to pi, you will obtain this, the ideal delay. So this low pass filter is allowing some band of frequencies whenever an input signal is given to such system. Okay, now we shall consider a couple of cases so that we can see some insights or some interesting properties of such ideal low pass filter. So say suppose we consider three cases. First one where we have omega c is equal to 0.4 pi, and you have alpha is equal to some integer as 5. Okay, the second case we shall see that omega c is equal to 0.4 pi, but alpha is not an integer anymore, it is 4.5. Now in third case we again kept the same frequency, cutoff frequency 0.45, it just we change alpha to some 4.3 value. Okay, so putting the first case omega c is equal to 0.4 pi and alpha is equal to some integer. So this is the plot you will see. Okay, so this is the figure A is for omega c is equal to 0.4 pi and alpha is equal to 5. So what do you notice here, that the impulse response, the amplitude is shifted by samples, 5 samples, and the middle point and lie here. Okay, so now if we see the impulse response, or so we see that first of all that the impulse response is symmetric, no, that the impulse response is symmetric around this point, and which is an integer, so which is good, and this we can analyze in the analytically also. So if I compute this HLP as 2nd minus n, where nd is my alpha, an integer is equal to 5, so in that case your impulse response is given by sine omega c 2nd minus nd divided by omega c minus nd, which is then simplified to omega c nd minus n and omega c nd minus n, right? And if you notice this is nothing but your impulse response of the low pass filter. So what do you see, that your impulse response is symmetric about nd. So in this case we could in fact define a zero phase system. So that zero phase system can be defined as some h hat lp e raised to power j omega as HLP, the actual low pass filter, times e raised to the power j omega nd. So I have shifted that signal, and this is nothing but the magnitude of HLP, right? Because the magnitude of this would be 1 since nd is an integer. So this is the interpretation what we were talking about. So here we have obtained actually the zero phase in the first case, right? Now if we see in the time domain of this h hat lp, it is given that small h hat lp times n as sine omega c n divided by pi n, which is nothing but h hat lp would be equal to minus n. So that's why it's a even sequence. Okay, now talking about the second case, which is this one, omega c is equal to 0.4 pi and alpha is equal to 0.5. So if we plot the impulse response of this sequence, so what do you see? that there is some symmetry in the impulse response. So here we see some symmetry around this point of the impulse of this impulse response. But this symmetry is not lying on the integer, right? It is not lying on some integer. So let's analyze this mathematically. This is for the second case. But another important thing is, since alpha is equal to 0.5, and in the above, similar to the above case, that twice of alpha would be an integer. So it is an integer plus 1 half, or 2 alpha would be an integer if alpha is equal to 0.5. So in that case, I can write HLP as 2 alpha minus n is equal to HLPn, because 2 alpha is an integer. So, and this is what we have observed in the figure, that the point of symmetry is alpha, and alpha is equal to 0.5, but it is not an integer. So since the symmetry is not obtained about the point of the sequence, it is not possible to shift the sequence to obtain an even sequence that has the zero phase. Right? So if we see from the first part, we had when alpha, or let's say alpha is an integer, which implies that the impulse response is symmetric about n is equal to nd. Right? Now in the second case, we see that it is symmetric about n is equal to alpha, which is not an integer, but it does not imply that alpha is an integer. Right? It does not imply that alpha is an integer. So it is not possible to shift the sequence to obtain an even sequence that has the zero phase. Right? Now if we talk about the third case, in the third case we have alpha is equal to 4.3. So twice of alpha is not even an integer. So twice of alpha is not even an integer. So you won't even see the symmetry in the plot. So this corresponds to alpha is equal to 4.3 with omega is equal to 0.45. So there is no symmetry. So if you see these samples, there is no symmetricity in the samples. Right? So the general thing to notice here is that if 2 alpha is an integer, the correspond, or let's say if 2 alpha is an integer, then the corresponding impulse response has even symmetry about alpha. That is, you would see that h of 2 alpha minus n would be equal to h of n. Now if 2 alpha is not an integer, then the impulse response will not have symmetry, and this we had seen in the cth figure. But in all the three responses, it has the linear phase, or equivalently the constant group delay. Okay, so we can close the lecture for today here, and in the next lecture we shall see the generalized linear phase. So here we saw the general frequency response with linear phase, but in the next lecture we shall see the generalized linear phase. Okay.